Today we'll be looking at Weil pairing. We've looked at everything required for this. We've looked at pairing groups. That's what we looked at last week. And so now we want to use those pairing groups to do now pairing, the Weil pairing. We have different types of pairing. Weil pairing is one of them and commonly used. Now, again, just a reminder of what pairing groups were. Of course, we'll be using them. We talked of pairing group G1. We also talked of pairing group G2. And before this, we had talked of a group which we call full arrow torsion group. Full arrow torsion group. Now, these two groups, we then agreed would be subgroups of this group. There'll be subgroups of this group. This full arrow torsion group was defined on the elliptic curve over a field extension of fields, FQK. Now, this came from the original field where this is FQ, where Q is just the mode, the characteristic of this field, So at some point, we then saw that we could get the embedding degree for this field. And if the embedding degree is K, then we come up with this field. Now, so the full arrow torsion group is defined on this field. So how are we getting the elements? How are we getting the elements? Once we have the elements of this field, once we have the elements of this field, we're getting those which, when multiplied by R, would give us the identity. So all those, when multiplied by R, all those points which, when added to themselves R times, would give us point at infinity, would form a full arrow torsion group. Will form a full arrow torsion group. Now, so out of this full arrow torsion group, we then came up with these two subgroups we called pairing groups, and those are the ones we'll be using today. How did we get G1? G1, supposing we go back to this K. How do we get K? So how we get K, first of all, we come back to this field. We find out how many elements this field has. If this field has 9 elements, we would then say, okay, the elliptic curve on this field. How many elements does the elliptic curve on this field have? So if the elliptic curve on this field has 9 elements, we would then get the divisors of these 9. For this case, only 3 is a divisor of 9. Prime divisor, not just a divisor, but prime divisor. Now, so this prime divisor 3 would then assist us to get K. Then assist us to get K. But now, without even going to there, G1, our G1 group is 3 torsion. Is 3 torsion group. So it's a group consisting of elements which, when multiplied by not just elements, but points, is a group. G1 is a group consisting of points, which when added 3 times, would give the identity. So that is how we got G1. It is 3 torsion group. If our elliptic curve were to have 9 points, if our elliptic curve were to have 9 points, then we would have G1 would be this group, 3 torsion. What about G2? Just again a reminder, our G2 would be comprised of points of this full R, in this case, full 3 torsion group. In this case, it will be full 3 torsion group. So our G2 will comprise of all those elements here that would satisfy the condition, and we call it Frobenius endomorphism the last time. Would satisfy the condition, the X value raised to P, the Y value raised to P will give you 5, or let me say P. Now, the first P is just a small letter for the characteristic of the polynomial. This first one here, FQ, supposing it's F5. So this first P is 5. And that one is the point. That one is the point. And so we would then be talking of X raised to 5, then Y raised to 5 should be the same as 5 raised to P. And we looked at this process last time. So all points that will fulfill this condition would form the G2 group. Would form the G2 group. So that is how we got the G1 and the G2 group that we are then are supposed to be using today. We saw the code for doing these groups, the code for computing group 1, G1, and group G2. And then it was giving us the elements of those, the points of those groups. Now, so while pairing, what are we going to do therefore? We have this group G1. This group G1 has elements, has points. One of the points is the point at infinity. And then we have another point and several other points. So that is, for instance, if it's 3 torsion, then we are only talking of 3 points here. So the point at infinity is one of them, then we have 2 other points. And then G2 would also have 3 points, the point at infinity and 2 other points. So while pairing, what we then are going to be doing, we pick one element from this group, another element from this group, and so supposing we have the map, and what the map is going then to be doing, the mapping elements of this group 1 cross group 2 to a target group, So that is what while pairing will be doing. So we pick one element from this group and one other element from this group. Then we use an algorithm, and that algorithm would give us an element of this target group. So that is what we then call while pairing. The most important thing again to remember is that the 3 groups have the same number of elements. They must be of the same order. Otherwise, it will not work. And the other thing to remind us is that the first 2 groups are additive groups. These are additive groups, but this one then is a multiplicative group. So multiplicative group, and then you know that the identity is supposed to be 1. And this additive, the identity is supposed to be 0. So when you're writing the code, for instance, you're writing the code, you're telling your code that the identity for this element would then be 0, 0. that is the point at infinity. X value will be 0 and the Y value will be 0. That is, and then this will be 1, 1. The X value and the Y value. So if you're telling your code, therefore, to note that every time you add and the result is 0, 0, because you'll be doing some addition, when you're multiplying by scalar, it means you're adding it the number of scalar. For instance, if you're multiplying 3 by p, you're adding p 3 times. That's what it means. So then you're telling it, if you add 3 times, for instance, or 2 times, and find 0, 0, it means you found the point at infinity. So the code then understands that. So therefore, what is Weil pairing? Of course, we had already defined the pairing, and we had said that it's supposed to be bilinear, supposed to be non-degenerate map. Bilinear, we say that it fulfills some conditions. There's a condition for bilinear. Of course, we said the condition will be that if you're given a p and pq, bilinear means that this will then go to this. This is what bilinearity means. And then non-degenerate, we said it means that it's important because it ensures that we do not have non-identity elements being mapped to identity elements. So it prevents that. We don't have non-identity elements being, so if P is not an identity element, we don't expect it to be mapped to identity. So those are definitions. That's how we define the pairing when we were beginning. So Weil pairing will then be defined on 2 groups. So we've already mentioned these 2 groups. The order in this case is R. So they have R elements. Group 1 has R elements and group 2 has R elements. And they're defined on full R torsion group. They're defined on full R torsion group of an elliptic curve. Normally, the elliptic curve has to be expressed in the short Weierstrass form. Of course, we've talked about several other forms of the elliptic curve. We talked about various forms. But if you want to do Weil pairing, then you have to use a curve, elliptic curve that is in short Weierstrass form. Of course, the other forms that we talked about, we said there are cases that are also used, and there are cases that are very secure. Of course, they are very secure. But now, to do with the elliptic curve, on the Weil pairing, it has to be in this form, not in the other forms we talked about. Now, so once you have the elliptic curve in this form, in the Weierstrass form, you only need to get G1 as we did last time and G2 as we did last time. And then Weil pairing will be defined this way. Now, the most important thing is, what is this? These ones, you don't compute them manually, but they are done using the Miller's algorithm. So that means as you write the code, you then must understand what Miller's algorithm is. And of course, we have libraries for this, for Miller's algorithm. So it will then be doing that for you. Now, just another important thing to note here on this definition, you can see that we have a denominator. We have a denominator there. That means that while you are doing this, we should then prevent doing division by 0. So every time you do division by 0, if whatever is here becomes 0, it means that there will be no inverse, because you're supposed to get inverse of this thing. Every time we've had something like this, every time we've had something like that, we've always gotten the inverse of the denominator and then written 3 times the inverse of the denominator. We've always done this. So you get the inverse of the, and then multiply by 3. So if the denominator becomes 0, then it means we would then not have the inverse. So it means that you cannot then get Weil pairing for that. So for this reason, then you find that Weil pairing can only be defined for elliptic curves that have the divisor of the number of the order. The divisor of the order should be greater than 3. If the divisor of the order is greater than 3, then you can get Weil pairing for that elliptic curve, for the points, for those points of those groups, these two groups. But if the divisor is 3 and below, then you cannot get. Because if the divisor is 3 and below, the likelihood of having divisors that are 0 is very high. And we shall see an example. We shall see an example. When the divisor is 3, it will not be possible to get Weil pairing. Now, so again, it's a very important thing. Weil pairing is a very important tool in cryptography. And it allows computations in the exponent. Exponent is just a power to be split into different parts. Now, the importance of splitting, you see, you're doing, for instance, you have, let me say, 35 raised to a very big number. So what then happens? You can split this exponent into several parts and then compute this 35 raised to the first exponent, 35 raised to the next exponent. Those exponents split into several parts. That makes computation faster. It makes computation faster. Splitting makes the computation faster. And that is the importance of that. So you can even split that exponent into different parts, and you have each part done by different parties, and then you merge the result. That now the code will be doing that for you. The code now will be splitting and then doing it, and then merging it, or it does it itself. Now, normally we do. I'd already mentioned that not Weil pairing cannot be defined on every elliptic curve. And I've just given an example that if for example, the divisor is 3 and below, Weil pairing cannot be defined there on that curve. Now, so therefore, the curves on which Weil pairing can be defined are called pairing-friendly curves. Pairing-friendly curves. Now, pairing-friendly curves are known. If you can even Google that, and they are known, so that when you're doing that for practical reasons, you just use Weil pairing curves for that. Don't just use any curve. Now, so I've said that an elliptic curve is considered pairing friendly if it has a prime factor of its group order such that there's an algorithm that can efficiently compute Weil pairing. So there must be a prime factor. The prime factor should be one that, and I've already talked of, for instance, if 3 is the prime factor, it will give us 0 in the denominator. And yeah, so we'll then be looking at the prime factor for us to tell if an elliptic curve is pairing friendly or not. So that we only use elliptic curves that are pairing friendly to do Weil pairing. You don't use any other. In practical applications, pairing-friendly curves will be those that have small embedding degree k. They have a small embedding degree k, and this embedding degree is always an even number. So it's either 2, or 4, or 6, or even 12. Not all even numbers, but in most cases, it's 2, 4, 6, and 12. So that means any elliptic curve that would have this embedding degree, any of these would then be considered a pairing friendly elliptic curve. At this point, I was just a recall of how we're getting the embedding degree, and of course, we've done this recall several times. Embedding degree has always been the smallest integer k that enables R to divide p raised to k minus 1. So that smaller k that would make it possible for R to divide this is what we call the embedding degree. We've always given examples. For instance, an elliptic curve that has 9 points, let me just use that, has R as 3, the divisor. That is the prime divisor of 9 is 3. So therefore, the embedding degree, and let me say that supposing we are working with the mode 5. Suppose you are working with the mode 5, the field is F5. So the embedding degree will be the K that will allow 3 to divide P raised to K minus 1. The smallest positive integer, K, that will make it possible for 3 to divide this. So as we've always done, we can realize that if K is 2, then 3 can divide 24. So the smallest integer for this elliptic curve, and we are then considering the elliptic curve x cubed plus x plus 1, which has 9 points. So its embedding degree, therefore, is 2. Embedding degree, therefore, is 2. Can you see the embedding degree is 2 there? But this is not, for this one, since our divisor is 3, this elliptic curve will not be pairing friendly. Will not be pairing friendly because of R, the divisor R. Although it has the right embedding degree, but the divisor is 3. So this elliptic curve is not pairing friendly. Now we need just to know what pairing friendly curves are, and then we proceed to do Weil pairing. Because we'll be using pairing friendly curves to do this, not just any curve. This point was just a reminder of what R is. Now, in cases where the divisors are 2, like for instance, we looked at this example, this elliptic curve, plus 8x plus 8 over F13, We found that we had 20 points. This one had 20 points. The prime factors of 20 are 2 and 5. The prime factors of 20 are 2 and 5. So therefore, R is supposed to be n of this, but now, for purposes of this, our R is always the largest of all the prime factors. The largest of all the prime factors. And there are cases where the prime divisors will be more than 1. The case that we had earlier, where we had 9 points, we only had 1 prime factor. But for this case, you can see we have 2. There are cases where we can even have 3 or 4 or 5 prime factors. But now, our R is always the largest of them all. Our R is always the largest of them all, not just not n of them, but the largest of them all. Now, why are we choosing the largest? And I've explained here. It ensures that the curve supports efficient cryptographic operations that involve pairing. If you take the largest will always ensure that the curve will support the efficient cryptographic operations. So the operations we are talking about addition, because we'll be doing addition, we'll be doing scalar multiplication, and so on. We'll be getting inverses. All those are required. And so if R is large, those operations can efficiently be done, unlike if R was a small value. Okay. So again, this is just an extension of that explanation. Still an extension of that explanation. Now, therefore, this point is just telling us where pairing-friendly curves can be applied. I've said they can be used in protocols like the ZK snarks, identity-based encryption, attribute-based encryption, and the short signatures. So in all these, you can use Weil pairing or you can use Tate pairing. Of course, there are various types of pairing. We began by looking at Weil pairing. So you can see where it's used. See, this is part of the areas we can use it. There are several other areas that we can use pairing. And these are the most areas that these are the areas that most applications have been done for pairing. Most applications. So again, we revisit properties of pairing-friendly curves. Properties of pairing-friendly curves. One, they should support pairings like Weil, Tate, and optimal efficiently. What is it? Okay, optimal at efficiently. Now, so in short, what I'm just saying is that we've talked of bilinear pairing. So bilinear pairing, the computation of bilinear pairing is supposed to be that pairing friendly curve should be one that can make this computation easier. Should be one that can make this computation easier so that we can efficiently do the computation. There are cases that we've seen one that has a denominator of 0. So if the denominator is 0, it means the computation there is not, it cannot be done. And the other one is that there should be They should have large embedding degree, and the embedding degree here would assist to prevent against attacks. Against attacks. And then we have what we call generation of prime order groups. So there should be one that can allow you to generate those prime order groups. So prime order groups that we're talking about here are just group 1 and group 2 that we've mentioned about at the beginning. So pairing friendly curves should be one that can assist you to come up with group 1 and group 2 easily. So that we have group 1 and group 2. And of course, you're not using the entire group 1 and group 2. We'll just be picking elements from one element from group 1, one element from group 2, and then we do Weil pairing. When we are doing Weil pairing, we do that easily, and we get another point from the target group. And we are saying that the pairing friendly curves should be ones that can enable computational group 1 and computational group 2 easily. Now, there are various types of pairing friendly curves. There are so many. It depends from one company to the other, one use to the other, where is it used, and so on. And so here I've just listed the popular, the most commonly used pairing friendly curves. The first one is the BN254 or BN128. So this is the BN254. Now, the B here would depend from one point to the other. So it depends from one use to the other. So it varies. It's not, so I didn't mention it because it varies. Another company would have a different value, and another one will have a different value. But the most important thing is that the curve will take this form. The curve will take this form. You are not seeing A. You're not seeing AX. It's not there. It's just X cubed plus B. But now this B would vary from one point to another point. So a different company would have a different B. Now, what about P? P here would be 254 bits. It's a very long number. This is a very long number. It's a prime number, 254 bits. The embedding degree for this, irrespective of the B you're using, embedding degree will be 12. Embedding degree K will be 12. Now, this one you can use it. You can find it in Ethereum, ZK Snacks. In Ethereum, in ZK Snacks, and you can also find it in these other protocols like Growth 16 and Long. These are just the protocols. So this is why it's commonly used. So that's why I said the B here would vary. So you find that Ethereum has its own B, and those doing pairing in ZK Snacks would have a different B, and even the Growth 16 would have a different, and Long would have, but the format would be the same thing. So if you're doing pairing there. Now, if you want to write a Rust code, you would then import these libraries. We import those libraries, and those ones will then assist you to do pairing using this curve, the BN254. Now, this is a commonly used elliptic curve, and you've seen where it's applied. It gets used in Ethereum. Ethereum use it. ZK Snacks use, and then Growth 16 and so on. The other one is this BLS12. 381 is another elliptic curve. This is an elliptic curve. This is an elliptic curve of this form. So this is x cubed and then plus 4. But now, the p there is 381 bits. 381 bits. And we have the embedding degree will be 12. And again, this can be applied in Ethereum, in BLS signatures, ZK snarks, and the Filecoin, and even the Algorand. Now, these ones you can just Google and find what they are. But this is a part of the areas that apply this. So they are applied in several places. And again, if you want to do Rust for this, you would use this library. And these libraries would then assist you to do that. Pairing here, pairing using this curve. Now, so I also chose to look at what to look at when you are choosing the curve. For example, if you are dealing with the Ethereum ZK snarks, then this will be the right curve for you. And if you want more security, you would want this curve. If you want to look at future-proof security, if you want to look at post-quantum research, you look at that curve and so on. So well, this is just a recommendation, but you can always use others. But now, these are the most recommended for these reasons. But there are various other curves that are pairing friendly. Now let's now look at an example of a Weil pairing, so that now we look at the code that it does Weil pairing, and we look at the first example. This example, we had already talked about it. This elliptic curve. This is the elliptic curve. Y square is x cubed plus x plus 1. This is done over F5. And we discovered that this elliptic curve has only 9 points. So the order is 9. So the only prime factor would then be 3. Now, we've talked about the prime factor. We say that this 3 would then prevent us from computing the Weil pairing using this Miller's algorithm. Remember, the Miller's algorithm was to give us F something. When we looked at the definition of Weil pairing. Look at the definition of Weil pairing. The Miller's algorithm is to assist us compute those elements. That is what the Miller's algorithm will be doing. But now, while computing the denominator, if the divisor is 3, the denominator would then be 0. Of course, the Miller's algorithm, you cannot compute it manually. It's a very long process. So it's better you do it using a code. So using that code, it will then give us to be 0 in the denominator. And therefore, it means you cannot do inverse. So say that since group G1 has order 3, this algorithm would lead to division by 0. And when that happens, then it means Weil pairing cannot be computed on this. Computed on that. So if you were to even get G1, get G2, and pick an element from G1, pick another element from G2, and try to do Weil pairing, discover that it's not possible. will not happen. Let's just see. So I have my code here. I have my code. Okay, this code I just made it specifically for that example. And then there's another code I'll share later. This one you cannot use it for various examples. Now, so this is a code I wanted to do while pairing for me. So I choose a point from G1. I've chosen P. And P is point 1, 1, 1, 1, 1T. This is a point. We had seen this. We had seen points in G1. When we did last time, we had points in G1 and points in G2. So one of the points in G1 was 1, 1T. So it's what I've entered here. And then this other point is 1, 4T. So what I've entered here. You remember how we're doing this? Remember how we're doing this? We were saying that a point in this on the extended field is supposed to be in the form A plus BT. A plus BT. So like the X value is supposed to be A plus BT. So like this one. This one is supposed to be 1 plus BT. 1 plus BT. But you can see B is 0. That's why you can see I've entered here 1, 0. 1, 0. Because it's supposed to be 1 plus BT. That is the X value. The X value. And the Y value you can see is just 1T. And it's supposed to be A plus BT. So it means A is 0, but B is 1. A is 0, but B is 1. You can see where I'm highlighting. A is 0 and B is 1. The same thing with the Q value, point Q. Point Q I've entered 140. It means B is 0 for the X coordinate. B is 0, and for the Y coordinate, A is 0. For the Y coordinate, A is 0. Now, so those are the 2 points. So I've entered point P and point Q, and I'm asking it to give me the Weil pairing of P and Q. So what I'm expecting, therefore, is for it to give me a value in the target group. For it to give me a value in the target group. And you remember this has the divisor is 3. Okay. Okay, so I asked it to give me several points. In fact, it began by giving me points. But now, when it comes to doing Weil pairing, you can see the denominator here. It says that there is no inverse. There's no modular inverse in the denominator. It panicked. The thread panicked. But at the points that we gave it used those points. You can see it has used points. Okay, first of all, it began by saying that the chosen points, the 3 torsion points, okay, I used it to give me several things. In fact, I began by asking it to give me points on the elliptic curve. So it gave me points on the elliptic curve. That was okay. But now, my main reason for doing it was to assist me now do Weil pairing. And it's telling me of the points on the elliptic curve. Because it has points on the elliptic curve. And on this elliptic curve, I had chosen this point. And I had chosen this point. I had chosen these 2 points. So that's why it's telling me that the chosen points, the chosen 3 torsion points are these 2. And now when it does the Weil pairing, it discovers that the thread panics. And the reason is because that there is no modular inverse for the value that it is in the denominator. So the value in the denominator becomes 0 when you do it, because it's doing the Miller's algorithm. So when it does that, it discovers that the denominator then gives it 0. So it's therefore not able to do that. Okay. I can just show you how this code looks like. The one that I've used. Of course, it's the same code we used to get three torsion group. I've only made a smaller change where I've asked it to give me the Weil pair at the bottom here. I ask it for the Miller loop. This is the Miller's algorithm. This is why I tell it to do it. So it will be converting a binary number to a string, then using that. So it begins to the function doing the Miller's algorithm is this. This is a function that will be doing the Miller's algorithm. So this is the only thing that I added, but the rest, the same code we've been seeing. Then I also added this other part, asking it to give me the Weil pairing. And then I'm telling it, you cannot give me Weil pairing without using the Miller's loop. So it's asking for the Miller's loop. The Miller's loop will be doing what we just said. Then it will be doing the denominator, the numerator, and then combining. So you can see we have the quotient here. We have let R be a point from the field. We began by defining the field above. Okay. So the rest of the code is just the same. The rest of the code is what we've been looking at previously. Even division, you see, here we've said a function for division. For division, you must first of all get the inverse of the denominator. Then how do you get the inverse? The inverse, I've explained how to get the inverse here. The same way we've been getting the inverse. Of course, we'll look at that later. We have talked about the Frobenius endomorphism, and it's here. This is just the normal exponentiation, fast powering algorithm. This is a fast powering algorithm. So you have a 10 raised to a value. How do you do it faster? This is fast powering algorithm. And then point at infinity. It must not at the point of infinity. How will it be written? If you get none, none. There's none, then none. Now it's at infinity. That is, if x is none, and if y is none, then we say that the point is at infinity. And last time we used 0, and the 0. There's no problem. You can always just change. You can always change the language, how you write it, but be consistent in the whole code. That there's that consistency. Okay, so let's continue the examples. But this is the example where the denominator is 0, and therefore we do not get Weil pairing. We do not get Weil pairing for the 2 points chosen. We have the other example we've been looking at, just been using two examples in most of our working in this topic. So we consider this elliptic curve now, where we have y squared is x cubed plus 8x plus 8. This one we discovered it had 20 points, and that the prime divisors of 20 are 2 and 5. And therefore, we are interested in 5. Our array is 5. So last time we did find the 5 torsion group as this. And also we discovered that the second group, which this group I've already mentioned when you are beginning, it's a group where the elements, the points P, supposing point P is xy, then this can be written as x raised to 5. No, not 5. In this case is 13, because our mode is 13. X raised to 13, y raised to 13. Now, so want points which x raised to 13, y raised to 13 will be the same as 13p. The same as 13p. So those points are this, and there will be 5. This 1, 2, 3, 4, 5. We looked at that in our last lesson. Now, so we want to do Weil pairing. So Weil pairing, it means we choose one point from group 1 and we choose one point from group 2, and then we do pairing and see whether we can get not a point this time, but an element of GT, our target group, an element of our target group. We don't get a point, we will get an element, the target group. Now, so we pick a point here, do Weil pairing. I want to see whether we can get an element of this field, where 4 is embedding degree. Must be an element of this field in the target group. Okay, so for purposes of this example, I've chosen this point and this other point. So this point is from G1 and this point is from G2. And I want to do my code and see what I get as a point, not a point, an element in the target group. See what element I get in the target group. Okay, so, okay, I'm dealing with let me just come here. I'm dealing with the F13. I'm dealing with the F13 raised to 4, where 4 is our embedding degree. So how do I expect how do I expect elements to look like? I expect elements to be like a constant. They look like a constant. You have A, and then BT, and then BT square, and then B. Oh, okay. So let me use C. ct square, then I expect it to be dt cubed. Okay, that's how I expect elements look like here. Because I know that anything more than 3, the power more than 3, and would be reduced because the polynomial that I'm using here is power 4. The polynomial that I'm using is t raised to 4, t raised to 4 plus 2. So it means, and I'm doing it mod 11. So if I was to take this on the other side of the equal sign, if I was to take to the other side of the equal sign, I will have t raised to 4 is -3, -2. -2 mod 11, mod 13 is 11, mod 13. So I expect elements to look like this. A constant plus b raised to t plus c raised to t square plus d raised to t cubed. But if you have t raised to 5, it will be reduced by this polynomial. To be reduced by this polynomial. So that is why this is why I've written this. This is why I've written this. Because this point was 7, 2. Let me just write it here. It was 7, 2. This point was 7, 2. But I expect the x coordinate to look like this. So how does 7, 2? So 7, 2. So A is 7. A is 7. That's the x value. A is 7. B is 0. So because it's supposed to be 7 plus, bt plus ct square plus d. So you can see 7 is 0, c is 0, and d is 0. So this one becomes a 7 because the rest is 0. Now we come to this other coordinate. This other coordinate, this other value, the x, the y value. Because we have the x value, the y value, the z value, and maybe the kth value, something like that. Now, so again, you can see this one. Everything is 0. This one, everything is 0. Because 7 was the x value, the constant here. But now when it comes to this other part, I have bt is 0, b is 0. And then when it comes to, where was that? It was 7, 2. No, it was not 7, 2. It was 7. Was it 7, 9? 9 what? Just go back to, just check. 90, okay. Q was 7, 90 square. 90 square. 7, 90 square. So this is constant t square, 90 square, then cubed is 0. Cubed, the constant for cubed is 0. For 9, this one was 9t squared. 90 squared. So 7 plus bt plus, so b again is 0, b is 0, and d again is 0, because we are talking of 9. We are talking of 7 plus 9t squared. Then this other part, is 2t and 12t cubed. I'm just confirming from the question. 2t plus 12, so it's supposed to be 2t plus 12 t cubed. So the constant, you can see that there's no constant here. So this is the x value. What about the y value? The y value is this. The constant is 0. Then the one that is multiplied by t is 2. And then the one that multiplied by t square is 0. The coefficient of t cubed is 12. Because it's supposed to look like something like this. Supposed to be something like this. The y coordinate should also be something like this. Yes, y coordinate is supposed to be something like this. So the x coordinate is this. The x coordinate is this. 7 plus 0t plus 9t square plus 0t cubed. And then the y coordinate is 0 plus 2t plus 0t square plus 12t cubed. So we just enter here. And the other one was 7, 2. The other one is 7, 2. 7, 2. So you can see, and again, coming back to this, the constant is 7. But now the one multiplied by t, bt is 0, because b is 0, and then ct square is 0, and then dt cubed is 0. Now we go to y coordinate. The y coordinate, the constant is 2, bt is 0, ct square is 0, and so on. Now, so that's just reminding you how you feed in your values. How you feed in your values. Now, I want to get Weil pairing for these 2 points. We do cut around and see what the result is. Okay, then it says Weil pairing is this. Just gives us the coefficients. Just giving the coefficients, but now we know how we were writing it. The constant was coming first. So this is 1 plus 9t plus 9t square plus 4t cubed. 4t cubed. So that's how we are doing this. That's how it's doing that. Now, so again, it's good to look at the code. The same code like the one we looked at. We imported the credits we required for this, the libraries. And then our prime is 13. So you can always change to your prime. That is, the prime here is the characteristic of the field. And then you get the embedding degree. Embedding degree here. So our embedding degree is 4. Because this group has 20 elements and P has 20 elements and our divisor of 20 is 5, 2 and 5, but we take the largest. So the largest is then 5. So we are asking ourselves, what value would make 5? Let me just write here. What value would make 5 to divide 13 raised to k, 13 raised to k, then minus 1. So what k can make it? So you then discover that if k is 4, 5 can divide this. 5 can divide 13 raised to 4 minus 1. So then 4 becomes our embedding degree. So this embedding degree will then assist us to come up with a polynomial. The polynomial we are reducing, and I've said in this question, the polynomial I'm using is t raised to 4 t raised to 4 plus 2, which is same as t raised to 4 minus 2. No, is equals to minus 2 mod 13. And so mod 13, this will be 11. So everything that goes, if anything becomes t raised to 4, t raised to 5, t raised to 6, I would then reduce it mod 11. No, 11 mod. I would replace it by 11. T raised to 4 would be replaced by 11. So that means t raised to 5, that means that t raised to 5 would then be written as t raised to 4, t raised to 4 times t, times t. But t raised to 4 is 11. So this becomes 11t. This becomes 11t. But if it is t raised to 6, this you can also reduce to t raised to 4 times t raised to 2. So that now t raised to 4 is 11, 11t squared. 11t squared. So that is how we then reduce it. That's how we are reducing this. So we cannot have anything more than t raised to 4. Every time it goes there, you reduce it using that. So the polynomial is very important here. So that all our powers will be in the range 0 to 3. 0, 1, 2, 3. Our powers will be reduced in this range. That is here, I'm referring to this. Our powers are reduced to in the range 0 to 3, 0 to 4, which us to then understands it will be 0, 1, 2, 3. Okay, so this is where I put our 11. This is where our 11 is. So this is then what you'll be reducing. Every time you have t raised to 4, it will be 11. T raised to 6, 11t squared, and so on. Now, this is where we're now reducing the coefficients. The coefficients. And remember those coefficients. For instance, let me show you. Let me show you something here. Supposing we had 4t raised to 6, 4t raised to 6. This, the code will understand it as 4, okay, 4t raised to 4, 4t raised to 4 times t squared, times t squared. So then it then understands that the first t raised to 4 is 11. T raised to 4 is 11. So this would be 4 times 11. 4 times 11, which is 44. 4 times 11, which is 44. I'm just reading here. This is 4 times 11. Then times t squared. Times t squared. And then after that, it then reduces this mod 13. 44 mod 13. So 13 goes there, and the remainder will be 5. Because it goes there 3 times, the remainder will be 5 t raised to 2. So that is what we'll be doing. Every time you get something like 4, so you're multiplying. So if your multiplication gives you 4t raised to 6, the code is able to understand it this way. And then this first bit. So this is what we talked about when we talked about the exponents being reduced. So you reduce the exponent, and then it's performed separately, and then the answers, you get a single answer after that. So you can see the exponents have been reduced. You can see the exponents here have been reduced. It was t raised to 6, but it has been reduced to t raised to 4 times t squared. And the t raised to 4 has been computed to be 11. T raised to 4 is 11, and then t squared remains as t squared. Then 11 times 4 would then be 44, which is then reduced to 5 mod 13. That's what when I talked of exponents splitting, that is what the code is then doing, splitting the exponents. Okay, we have a part for doing the inverse, a part for doing the inverse, just the same way we've been doing, and you can see this, you can see what does this mean. So what that means is that if I have a number and then I multiply by its inverse, the result is to be this. So if the result is this, then it means those two numbers are inverses of each other. If the result is this, what is this? This is just, we said elements of this code, we say they should be in the form A plus BT plus CT square plus DT cubed. So then we're just saying the inverse is 1 because BT is 0, CT square is 0, DT square is 0, and the only constant we have is 1. So our A is 1. So when you multiply two elements, which are inverses of each other, then the product should be 1. I'm just checking if I can get an example just to illustrate that. Okay, maybe if we meet it, we can do it later. But I can show you how to get an inverse of a number. Let me just, I'll show you later, show you how to get the inverse. Or how to prove that two numbers are inverse. So you just multiply them. And then if after multiplying, you check to see what the product is. And if the product is 1, then it means that they are inverses of each other. But the product is not 1, it means they're not inverses of each other. Okay, so yeah, I have an example here. I just want to show you an example. An example of two elements that are inverse of each other. Okay, this is just explanation of the code, but I'm looking for space just to show you how to get inverse. Okay, I think this space is enough. Now, 04011, I was able to cite this as inverse. And supposing D is 04011, and I want to see whether its inverse. I want to see whether its inverse is 01201. 01201. I want to see whether its inverse is 01201. Now, so I want to see whether the inverse is that. So just multiply. What do you understand by this? This is 0 plus 4t plus 0t square plus 11t cubed. And this is what you're multiplying by 0 plus 12t plus 0 plus t cubed. T cubed. And you want to see whether you can get 1. So you just multiply 0 by all this, 0 by all that to give us 0. Okay. Then what about 4 by all this? 4 by the first one will be 0. 4 by the second one. Okay, just check. Okay. 4 by the first one will be 0. 4 by the second one will be 48t square. 48t square. And 4 by this one will be 0. 4 by this one will be 4t raised to 4. 4t raised to 4. Yes. Okay, what about 0t square by all of this will be 0. Okay, let's leave that. What about 11t cubed? 11t cubed by this will be 0. 11t cubed by this will be 132. 132 t raised to 4. T raised to 4. Then this will be 0. And this will be 11 t raised to 6. 11 t raised to 6. Then we just reduce. We remember our polynomial t raised to 4. T raised to 4 will be giving us 11. T raised to 4 will be giving us 11. And anything, a coefficient that is more than 13 will then reduce it. We have nothing to do here, so we leave it. 48. 48, we reduce 48 more 13. 48. Okay, 48 divided by 13. Oh, what have I used? Divided by 13, go there 3 times. Go there 3 times. And the remainder is 9. So this becomes 9t squared. What about this? This is the same as 411. Because t raised to 4 is 11. What about this? 132. 132 raised to 13 goes there 10 times. So the remainder is 2. The remainder is 2. This is 2. But now this one is 11. This one is 11. T raised to 4 is 11. But this one is 2 more than 13. This is 11. Okay. Now let's come here. This is 11. T raised to 4 times t squared. And we know what t raised to 4 is. T raised to 4 is 11. So this is just like 11 times 11 t squared, which is 121 t squared. 121 t squared. So what is 121 mod 13? What is 121 mod 13? Was there 9 times? The remainder is 3. So this, the whole of this is 3t squared. 3t squared. Now, so what do we have? We have 9t squared and 3t squared. That gives us 12t squared. Okay. Is it 12 really? Okay, just a minute. That was okay. This is 9. Let's come here. Let's come here. Let's come here. This was 11 t raised to 4. Okay, that is 11 times 11, 121, divided by 13. Was there 9 times? The remainder is 4, not 3. The remainder is 4. It's supposed to be 4, not 3. So 4 plus 9 will be 13. 13t squared. What about this? That is 44 plus 22, which is 66. 13 into that it goes there 5 times. It goes there 5 times. 5 times. The remainder is 1. So this is the same as that. But this is 13t squared. 13 into 13, the remainder is 0. So this is 0t squared plus 1. So that is 1. So it means this and this are inverses of each other. And that is how you compute, that's how you prove that this. So the code will be doing that. The code, we've been managed to do this manually, but the code will be doing that just to, of course, the code will be calculating the inverse of. So to calculate now this inverse, use the extended Euclidean algorithm. Use the extended Euclidean algorithm. But here we've just verified. So how do you use extended Euclidean algorithm? The code, so you must know how the extended Euclidean algorithm works for you to write the code that will be doing it. Because the code is supposed to find the inverse. The code is supposed to find the inverse. Let me just show you how you then be giving you the code. How you writing the code. The code that is then supposed to do the extended Euclidean algorithm to get this inverse. But we just proved that these two are inverse of each other. So how do you get, supposing you didn't know that this is the inverse, then you must then understand that the inverse of this number, you must then understand that the inverse of this number is another number, a plus bt plus ct squared plus dt cubed, such that this product gives you 1, 0, 0, 0. So just multiply and then equate to 1, 0, 0, 0. And solve for A, solve for B, solve for C, and solve for D. So for instance, multiply by 0. So you will then collect the like terms. Those that have t's together, collect them together and equate to the constants shall be collected, and then you equate the constants to this 1. And then those that have t, collect them after multiplying, then equate them to 0. Those that have t squared, after multiplying, collect them and equate to 0. Those that have t cubed, after multiplying, collect them and equate to 0, and solve for the coefficients. For instance, if I multiply by 0, I would have the entire thing 0. So that is a constant. Then I would multiply by 4. Multiply by 4. I would have, first of all, 4 times a would be 4. 4a, that is a constant. And then I would have a 4bt. Then I would have 4ct squared. Then I would have a 4dt cubed. Then let me multiply by this 0. Again, if I multiply by this 0, I get 0. Let me multiply by 11. I would have 11a plus 11bt plus 11ct squared plus 11dt cubed. So what are the constants? Constants are this 4a and 11a. Equate them to the constant 1 and solve for a. Solve for a. Let me see what will happen. If I was to multiply, to add them, for instance, this would be 15. 15a equated to 1. Of course, what is this? 15 is 2. Is 2 mod 13 equated to 1. So what is A? A is the inverse of 2, mod 13, and so on. So again, this is just an example. Then again, add. I've not said that this will be the only constants, but I've just taken these two examples. Just taken this 0, 4a, and 11a. Maybe there could be other constants. Now equate those that have b, that have t. Those that have t. Add them, and then equate them with 0t. Then find b, and so on. So when you do that, you should be able to get our inverse. So that is how the code will then be working to find the inverse. So first of all, it has to understand how the elements of this field would look like. How the elements of the field would look like. So you define how the elements of the field would look like. And let me again go back. So where are we defining that? So here we are defining how the elements of, okay, these are different. But it is the same thing. The same thing, we begin by defining how the elements of the field look like. So that as it begins, it then knows how the elements will look like. Let me just go back to where we have defined that. Okay, you've also defined the identity element. For the additive group, the identity element looks like that, and then it looks like that, the X and the Y values for the additive group. Okay, here you just limit how to multiply, how to add, how to subtract, and so on. And then you give it to the Miller function. The Miller function, we said what it will be doing. And then you ask it to do Weil pairing. Give it how it will be doing the Weil pairing, then you give it the points. It should be able to do that for you. It should be able to do that for you. Now, look at this. At this point, we are telling it how to double points. For instance, if you have 5p, want to have 5p, you'll have p plus p. That is point doubling, p plus p. So you're telling it how to double. And if it's identity, again, how it's supposed to know that this is an identity element. Okay, so I think I should, okay, this is the identity for multiplicative inverse. No, for the multiplicative group, the identity should be 1, 0, 0, 0. But for the additive group, the identity is 0, 0, 0, 0. I think I should stop there. Then maybe we can again revisit it next time. But for today, I think let's stop there.
Okay, thank you, Mwalimu. I think we can continue tomorrow, maybe.
Okay.